Yay!
Yay! Hey everyone, let's do a quick example of a problem that you're going to see over and over and over again, probably. And this is two objects that are tied together by some sort of like rope, and one's on a table and one's over a pulley. And this is going to illustrate a couple of techniques. This is a pretty simple example compared to maybe what you have already seen or what we will be doing. But there's a couple of techniques I just wanted to go over real quick because it turns out they're subtle, but they're important. All right, Newton's second law, what is it? It's when you sum all the forces together. Remember, I'm trying to be kind of careful how I say it. You sum all the forces together, they're all vectors, and that equals the mass times how the thing accelerates, right? So that's going to be our task, is that we're going to sum the forces together in every direction and try to solve for the acceleration. In this case, the acceleration of the system. All right, our strategy is always the same. For each mass, we're going to do this. So we're going to split it up. It's useful to split this up into the x direction and the y direction. So, all right, let's do M1. Look in the y direction of M1. I'll do this direction first. So for M1, what do we have? Down is gravity, right? We do a little free body diagram. M1G is going down, and then up is the normal force. That's all that's going on. And in this case, so for M1 in the y direction, I've got n minus mg equals 0. So this is telling us the usual thing, that the normal force is just equal to mg. Now, it turns out that that's not even going to matter because we're not going to need it. But anyway, this is sort of a classic thing. If something's just resting on a horizontal surface, usually n is equal to mg. Okay, so now let's do the x direction. In the x direction, what are the forces on this mass in the x direction? Well, it's a frictionless. Did I already say that? No, frictionless. It's a frictionless tabletop. We'll put friction in next example, right? Let's keep it simple. So the only force in the x direction is just going to be this one. The mass feels this. Tension, right? In fact, I'm just going to put T1 tension acting on mass 1. That's it. Okay, so summing the forces is easy. I just did it. There's one, right? It's easy to sum one thing. So T1 is acting to the right. That's it. So that must equal MA, right? M1 times A. Okay. Well, that's all there is to that. We're kind of done. We're done with M1. How about M2? In the y direction for M2, look at this. This is what's cool, is that we can treat these totally independently, right? The x direction for M1, the x and y directions for M2, they're totally independent. And then we'll tie them together in kind of an interesting way. So each one can have its own coordinate system, it'll turn out. Okay, so the y direction for M2, what do we have? What does M2 feel? M2 feels tension pulling up on it, and then it also feels gravity pulling down. Okay, and that's going to be it, right? So T2 minus M2G is equal to, oh, you gotta watch it. Some people are going to be tempted to set that equal to 0. We kind of did that on mass 1, right? That there's no acceleration in the y direction. But look here on M2. Is it moving in the y direction? You bet, because when this thing starts sliding, M2 is moving, it's accelerating in the y direction. So that's not going to be 0. That's going to be equal to M2A. Oh, and I wasn't careful enough. Let's see. This is going to be A1, and that's A2. Right? We'll make sense of this in just a second. So let's just be really careful with the symbols. All right, and in the x direction, all right, nothing's going on for M2 in the x direction. So here's what we've got. We want the accelerations, right? So that's going to be M1 in the x. That's got an A in it. And then m2 in the y has got an a in it. So here's what we've got. We have T1 is equal to M1 A1, and T2 minus M2G equals M2 A2. I'm just copying the equations I have down below. Okay, here's a couple of tricks. Here's how we're going to do it. When you do these problems, this is called an ideal cord or ideal rope. And all that means is we're considering this to be like fishing line or something, something that's got a negligible mass compared to the masses of M1 and M2. So that cord, we don't even care how much the cord weighs. Why might we care about it? Well, it's not always true. It's an approximation, because what could happen, look, if M1 starts sliding over to the right and M2 starts sliding down, there's more rope hanging vertically than is horizontally, right? So what might happen if the rope is really heavy, then you have to worry about that there's more weight on the right-hand side than there is attached to M1. So the weight gets bigger the more it kind of falls down. But we're not going to worry about that. That's kind of a negligible thing we're saying. So it's an ideal cord. There's no weight of the cord at all. And it's not stretchy. There's no weight. And it's not stretchy. What I mean by that is M1 doesn't accelerate relative to M2. They stay the same kind of distance apart, right? The rope doesn't stretch, is what I'm saying. So in that case, here's what we can do. In that case, that implies that T1 equals T2. The tensions are the same. All the pulley does is it just redirects that force. And you might be worried about those arrows going in the same direction. The trick is, and this is a difficult thing in physics to really get your head around, tensions in a rope are everywhere in both directions, right? Because what does the pulley feel? If you're on the pulley, what the pulley feels is the pulley feels a tension that way and a tension that way, right? So everywhere along the cord, you get tension forces acting in both directions. We're only interested in the forces on the masses. So we're only interested in T1 and T2 in the directions that I indicated first. So what we can say is that the magnitude of T1 is equal to the magnitude of T2. So in that case, let's just call it T. So all the pulley does is redirect it. It's the same force, same magnitude of force, different direction, right? But we're taking the directions into account with our plus and minus signs, so it's the same magnitude. So instead of T1 and T2, I can just call it T. All right, that's simplification number one. Number two is look at the accelerations. How are we going to tie together A1 and A2? They're related to each other. A1 and A2 had better be the same in magnitude, right? If they're not, then the rope is getting stretched. Then one is accelerating relative to the other one. So that's not the case. So A1 and A2 have to be the same magnitude. But look, when this thing accelerates to the right, what is A2 doing, or what is M2 doing? M2 is going down, and that direction we've called negative. So when A1 is positive, when M1 is going to the right, which we called positive, M2 is going down, which we called negative. So how we're going to take care of that is A1 is equal to minus A2. I'm just going to call that A. So this is how we're going to tie those masses together. Formally, these are called constraints. So when A1 goes to the right, A2 goes down. But this is how we're going to tie them together. So here's what I can write. Look at this. This means that T is equal to M1A, right? Getting rid of those subscripts. And then the other equation is T minus M2G is equal to minus M2A, right? It's the same A, it's just minus. It's just got a minus sign. Very cool. All right, so what I can do is solve for that T and plug it in there. Boop. So let's do that. T is just M2G minus M2A. So M2G minus M2A equals M1A. Nice. So M2G equals A, M1 plus M2. If I bring it over to the other side, factor out the A. Okay, so I'm done. My acceleration is m2 over m1 plus m2 times g. That's the acceleration of the system. And so you can plug in individual masses. I mean, just for kicks, let's say that m1, what did I use before? M1 is 5. Oops. Hand slipped. M1 equals 5, M2 equals 10 kilograms. And so if I do that, what's my acceleration? It's this would be 10 over 15 times g is like 10, pretty close. So this is something like a is something like 6.7 meters per second is how fast this thing is going to accelerate. And then if you want, you can go ahead and find the tension. What's the tension in the rope? That's kind of an interesting thing. The tension in the rope is, what was it? M1 times A, right? Well, there's my A. Multiplied by 5, what do I get? 33 newtons. Very cool. So this is how we're going to solve. I went through a lot. This is a lot longer than it needed to be. But I wanted to illustrate a couple of these tricks because we'll just kind of blow right by them in the future. Tensions are the same along a rope as long as the masses are not accelerating. In a pulley, as long as it's an, I didn't mention, it's an ideal pulley, right? A massless pulley. We'll do massive pulleys a little bit later. But for an ideal pulley, when you just, and all the pulleys we have right now are going to be ideal. So tensions just change direction, but not magnitude around a pulley. So all the tensions are equal in magnitude. And then we tie together those accelerations because the rope doesn't stretch. So those are a couple of things to keep in mind as we go on. But that's a fairly simple example. What remains is to do things like, well, now what if they were on an inclined plane? What if there's friction, right? There's all sorts of ways we can sort of jazz this up. So that's what we're going to do next.